It's my great pleasure to introduce our next speaker, Professor Tom Goldstein from the University of Maryland. Tom is currently as an associate professor of computer science at UMD. His research lies at the intersection of machine learning and optimization and has with many applications in computer vision and signal processing. Before joining the faculty at Maryland, Tom completed his PhD in mathematics at UCLA and was then a research scientist at Rice University and Stanford. Tom has really done fantastic work in many areas. He's really well known for his work in split Bregman and later on for the analysis of the landscape of deep networks. But over the past years, he's really become a leading figure in adversarial learning and making sure that neural networks are robust to adversarial perturbations. He has received many awards for his work, including the SIAM's DiPrima Prize, DARPA Young Faculty Award, and a Morgan Fellowship, and he's also a Sloan Fellow. We are really delighted to have you, and welcome, Tom.
Thank you very much, Renee. Thanks a ton for the invite. I was really excited to have a chance to speak at this workshop. There's a lot of great talks, and a lot of the content's been really interesting. So I'm glad I have a chance to contribute. All right, so I'm going to tell you guys a bit about some of the work we're doing in my lab on adversarial attacks. And in particular, one thing we're interested in is, adversarial attacks, a lot of them have been demonstrated in many different settings, but often on these more academic data sets, like simple classification problems. And so we're kind of curious, how well do these things scale up to say, industrial systems? So a lot of the adversarial attacks that you might see are things that look sort of like this. So this is an example of ResNet 50. ResNet 50 thinks this is an Egyptian cat with 28% accuracy. The reason it's only 28% confidence is because there's many different kinds of cat, and this confidence is sort of smeared out over the different cats. But a small perturbation makes this into a 97% traffic light. And so these kind of attacks have been demonstrated many, many times, and with various attack modalities. But the question we're interested in is, how far do these attacks go, right? These sorts of simple image classification problems are the sort of thing that you see oftentimes in an experimental lab. But then what happens when you actually try to attack industrial systems? Industrial systems use more sophisticated kinds of, for vision at least, more sophisticated kinds of scene analysis than just a simple classifier. And there's all sorts of different difficulties you might have to overcome to actually attack industrial systems. And so there's a few different kinds of attacks that we're going to look at today. The first kind of attack we're going to look at are called digital world attacks. In the digital world, when I say the digital world, I mean that you're going to attack a digital object like an audio file or an image, and then you can directly hand that image off to a machine learning system. Digital world attacks are the most, in a lot of ways, the most dangerous kinds of attacks. I think that the literature tends to have a focus on physical world attacks, where you actually modify an object, like putting a sticker on a stop sign. We'll talk a bit about those later. But physical world attacks are actually really difficult to make work reliably. And I think some of the most dangerous attacks are in the digital world. I'm going to show you a few examples of attacks in the digital world that I think are actually quite interesting, even in industrial settings. Okay, so the first thing I want to look at is face recognition. So there's been a lot of concern lately about the use of face recognition systems, and in particular about people's face images and personal information being harvested without their consent. Very often, I think the discussion around these types of topics focuses on social networks like Facebook, but I actually think that in terms of leaking people's personal information, the worst culprit might actually be LinkedIn. LinkedIn, you don't even need to log in to be able to scrape huge amounts of personal information, including people's photos, people's job titles, their education history, and in particular where they live, which makes it fairly easy to build face recognition that can recognize large numbers of people if you have this sort of address information. And what happens is there's firms that will scrape this information from the web. For example, this company Clearview AI has been in the news quite a lot recently. It's been very controversial. They scrape people's personal information and they build these databases with hundreds of millions of Americans. And then they sell your identity without your consent to private companies, political organizations, law enforcement, foreign governments in some situations. And so there's a lot of concern about the ethics of doing this and whether there's mechanisms that you can use to subvert these kinds of mass identity harvesting campaigns. In the academic literature, one thing that's come up recently is the system FOX, which is designed for modifying images with adversarial attacks so that they will not be recognized by face recognition systems. And they've had some success, at least in sort of academic settings. So at attacking image classifiers, in particular on small data sets, I think this is an interesting proof of concept. But what we're interested in is how well do these kinds of adversarial attacks actually scale up to defeat industrial systems. So is it possible to make perturbations to your face images before you put them online that will help prevent companies from using them in face recognition systems? Okay, so here's a simple schematic of how a face recognition system might work. So an industrial scale system usually works by doing feature matching using something like a Siamese network. So you have what's called a gallery image. So this is what Clearview might scrape from the web. It might scrape this from your internet profiles. You push these through a neural network and you create a feature, and those features get embedded in feature space. And usually you want them to be clustered in such a way that all of these different identities produce images that lie in similar locations in feature space. So you scrape the web, you produce a whole bunch of these images of Yoda, and then at test time, you get a probe image. So this is something that might come from, say, security camera footage or video that's acquired in a public space. You run some sort of localization and alignment to extract the face. You push that through a neural network, and then you see where the features land in feature space, and then you'll do some sort of feature matching. So in this case, you say, well, this image lies really close to all the Yoda images, so this is probably baby Yoda. So the idea behind the LOWKEY system is that we're going to add an extra step in here. So before the gallery images get scraped, you push them through this LOWKEY system and you make adversarial perturbations to them that will move them to different locations in feature space. So now all of the gallery images lie in fairly unusual locations in feature space. And now when a probe image comes along, right, you don't have control over the probe image, but it no longer maps to a region that's populated with your social media images, and that makes it very difficult to identify you. So how do we actually go about creating an image? We solve an optimization problem like this. So we start with the base image, B, that's your image, and you stick it through a neural network. So you have a feature extractor, F, that we want to measure the relative difference between the perturbed image, the features for the perturbed image, and the features for the base image. So I want your perturbed image to lie as far as possible from the base image as it can in feature space. And at the same time, we want it to lie close to the original image in some metric. In this case, we found that this LPIPS metric, which is a perceptibility metric, is a really nice way to measure the disparity between the attacked image and the base image. And if we do that, we can come up with images that defeat a face recognition system. But that doesn't necessarily mean that it scales up to industrial systems, because industrial systems have a lot of complexities. They're usually black box systems. I don't know the details of exactly how they work. And so in order to scale this up to black box systems, we ensemble over a number of different factors. So we will train to create an image that will defeat a range of different architectures with a range of different backbones. And we also augment with a range of different distortions like blur, JPEG encoding, and random cropping to deal with the fact that there's going to be a face localization and extraction step. And so we look at systems. All of the systems that we're going to show in our experiments here were trained on this MS-Celeb1M data set, has about 5 million images in it and several thousand identities, and then deployed on a different data set, because in reality, with face recognition systems, you don't have the luxury of testing on the same distribution that you trained on. Okay, so this is an example where we took those trained systems, and then we try to see whether or not we can recognize identities from the face scrub data set, which contains a very large number of distractors. So there's only 530 labeled identities, but there's also many, many distractors. There's about 1 million distractor images that represent other identities that you have to discern between. So this is a fairly large scale test. And what we find is that Amazon Recognition API is a publicly available API. It's a proprietary API developed by Amazon for face recognition. And we find that this gets a top 1 accuracy on face scrub of about 93.7%. So 93.7%, it can identify that the top match that comes out of Amazon Recognition is the correct identity. If we compare to something like Fox, this is another system that's been proposed. That degrades it to about 77.5% accuracy if we use the largest perturbation, the most aggressive attack that is allowed with inside of this Fox library. And then if we look at LOWKEY, LOWKEY can actually reduce the top 1 accuracy of Amazon recognition to about 0.6%. Now that's the top 1 accuracy. In face recognition, very oftentimes people don't use top 1 accuracy. People will use something like top 50 accuracy. And there's a reason for that. It's because, you know, if law enforcement or some other entity wants to identify somebody, they don't have to just rely on the top 1 match. They could look at the top 50 matches and then do some sort of, you know, human inspection to try to see whether or not they found the right identity. So Amazon recognition, their API actually gives you back the top 50 matches. Top 50 our LOWKEY framework will degrade performance of Amazon recognition to about 2.4%. And then on Microsoft Azure Face, this is another industrial API. The clean label accuracy on this, not sure why this bar came out where it did, but the clean label accuracy on this system is about 90.5% accuracy, so a little bit less than Amazon recognition. Fox can degrade that to about 75%, and then LOWKEY can degrade that to about 0.1%. This API does not provide top 50, so we're just reporting top 1 accuracy. So here's some examples of LOWKEY images. So at the top, we have the original images. At the bottom, we have perturbed images. And interestingly, we don't claim that LOWKEY images are imperceptibly modified. The modifications we make to them are oftentimes fairly small, but if you look carefully at these, you actually can oftentimes see the modifications, at least on these images, which are perturbed severely enough that we can defeat industrial APIs that have proprietary implementations. Okay, so here's another interesting example in the industrial space where these kinds of recognition systems are used for things like content detection. So we have these tools like YouTube's Content ID, which detects copyrighted content, Google Jigsaw, which detects illegal content that's posted to Google. You have apps like Shazam. There's this online system called Audio Tag for detecting copyrighted material. And a question you might ask is it possible to defeat these things with adversarial audio? Or can you make adversarial songs that cannot be detected by these copyright detectors? And so interestingly, you know, most of these systems today probably use convolutional networks. And we're pretty confident that we can defeat convolutional networks, at least in a white box setting. One thing we thought was interesting is that the Shazam, the people who developed Shazam actually have an old paper that they published from the pre-deep learning era that shows how the Shazam algorithm worked. It's a simple hashing algorithm. I'm just to actually see if we could attack that algorithm. And it turns out that you can actually reinterpret the original Shazam algorithm as essentially a neural net feature embedding. And one of my students, Parsa Sadapana, and also with the help of my student Ali Shafahi, who's recently graduated and is now at Apple, they built a differentiable Shazam in TensorFlow by essentially implementing all of the operations inside the algorithm as things like convolutions and max pooling, and they can backprop through this system to create adversarial music. So on my website, you can see some of the examples of this music. If we do a white box attack, we can make imperceptible perturbations to the audio, things that even with a really good audio system are very difficult to hear, and we can defeat a white box system fairly easily. A black box system is a bit more difficult, and to see whether that's feasible, we decided to scale up the perturbations we created on this handcrafted feature system and see how they would work against an industrial system. And we find that we can break these industrial systems with a perturbation about 5 times smaller than you could if you just add a random perturbation to the audio. So here's an example of uploading the song Signed, Sealed, Delivered, I'm Yours by Stevie Wonder. If we upload the original to YouTube, it generates a copyright claim, but if we upload an adversarial example, it does not. And we can do something similar with the audio tag system. Another application we've been recently interested in is this concept of attacking financial trading algorithms. So if you look at an exchange like NASDAQ, it turns out that almost all of the buy and sell orders on NASDAQ are actually placed by bots. They're placed by algorithmic trading bots. And many times these bots are actually using what are called valuation models. So they're essentially trying to predict future prices in order to make intelligent decisions about when to place buy and sell orders and by how much or at what prices. Right, so we're looking at this task of doing future value prediction. So we're going to look at a 60-second snapshot of stock market data, and then we try to predict 10 seconds in the future, what is the value of that symbol going to do? Is it going to go up, down, or stay the same? Now, this is a bit different than many of the digital world attacks that we've seen. I said digital world attacks are really dangerous because you can hand the perturbed data directly to the victim. So you can bit for bit control exactly what the victim sees. But in this case, there's something else going on that also gives power to the attacker, and that's that the adversary also has access to the training data. So for example, if we try to attack Amazon recognition, that could be difficult because I don't actually know, not only do I not know what architecture they're using, but I don't know what training data they use to produce their system. But in this case, firms are usually just training on historical stock market data, and everyone gets access to the same historical stock market data, maybe with some variations in the temporal resolution, but everyone sees pretty much the same thing and trains on pretty much the same historical data, and then makes predictions using pretty much the same inputs, right? So this gives you a lot of power as an attacker. So we set up an interesting test problem. So we look at, let's say, a candlestick chart that shows the value of the stock over time. And then at the end of a 60-second interval, we're going to predict 10 seconds in the future, what is the value of this stock going to do? Is it going to go significantly up, significantly down, or is it going to stay roughly the same? And we set the cutoff thresholds for these up and down predictions so that this is a balanced classification problem. About 1/3 of the time, the stock price goes in each of these directions. Okay, so here's some example results. We look at a few different stock symbols in our paper, and this is just one in particular. But using something like an LSTM model to do future stock value prediction, we can actually build a model that gets 36.4% accuracy on this prediction task, which, remember I said a random guess is succeeds 1/3 of the time. So 33.3% is a random guess. We can get 36.4%, which is actually considered to be a pretty good margin in the stock market. And by making adversarial buy and sell orders, so if you place some adversarial buy and sell orders into the order book, we can actually degrade that accuracy down to 21.76%. And the total value of all the buy and sell orders we place is a little over $10,000. And I would point out that in order to place these buy and sell orders, you don't actually have to spend this much money. It could be that some of those buy and sell orders could get canceled before they're executed. We actually have an algorithm that can place and remove all of these sell orders before they're executed. But if all your trades got executed, this is the amount of value that would be exchanged. Of course, if you spent this much money in dollars, that money wouldn't disappear. You would just now own this much Ford stock. Or if you own this much Ford stock to begin with, you would just convert it back into dollars. Okay, so those are some examples of digital world attacks. We're also interested in physical world attacks. Now, I pointed out that physical world attacks are quite difficult compared to digital world attacks. In a physical world attack, you're not actually attacking a digital object like an image. You're attacking a physical thing. So you want to perturb a physical object and then hope that when a measurement of that object gets taken using, for example, a camera, that the perturbation you made remains adversarial. And one of the reasons this is difficult is not only because you don't know what the sensing modality is exactly, but because you don't know what the scene is going to look like. You might not know what the lighting is going to be like, or exactly what the position of the object will be when it's imaged. You don't know what kinds of occlusions there will be, and so it's much more difficult to attack things in the physical world. There have been some early demonstrations of these kinds of things on academic systems. So there's this well-known Eckeholt paper where they show that adversarial graffiti can defeat these stop sign classifiers. And there's also been this paper, Accessorized to a Crime. I always admire when a paper has a great title. This paper has a great title, Accessorized to a Crime, where they show that you can make adversarial glasses that will change your identity according to a simple face recognition system. They actually use a simple face classifier with a relatively small number of identities. They don't deal with things like face localization and extraction, and they don't deal with things like a large-scale Siamese net like you might have in an industrial system. Right, so these are simple proof of concept attacks, but they don't necessarily scale to industrial systems like object detectors. And so one thing that we've been interested in is, can you actually defeat an object detector? An object detector is much more complicated than an object classifier. Those two things are different. A classifier just assumes that it assigns one label holistically to an entire image. So it might look at this and say, that's an image of a dog. Whereas an object detector might look at the image and say, there's a bounding box here with the dog, there's a hand, there's a box, right? It'll break an entire scene down into its components. Also, object detectors have a much more complex ensemble behavior that makes them difficult to defeat. So the way that a simple detector works, for example, the YOLO detector, the way it works is it looks at an image and then it outputs feature vectors at many different locations. So it looks at a 60 by 40 grid of possible locations in the image. And at every one of those locations, it looks at 9 different bounding boxes. So it looks at 3 small, 3 medium, and 3 large bounding boxes. And it tries to determine whether there's an object in them. So you've got a 60 by 40 grid of locations and 9 bounding boxes at each of those. So it's looking at about 21,000 bounding boxes spread over the entire image. So you might look at this dog image and you might end up with something like this. You've got a whole bunch of different bounding boxes at different locations that all think that they see that dog. Obviously, some of these bounding boxes will be better than others, and so you then do something called non-maximum suppression, which is essentially throwing away all the bounding boxes that aren't the best. So it'll take the most confident bounding box and it'll toss out all the bounding boxes that are less confident and overlap with it. So it removes those redundant detections, and then you end up with this single bounding box that detects a dog. But this non-maximum suppression step makes it really difficult to attack detectors. So you might have, say, 500 bounding boxes that all detect this dog. Now you can add an adversarial perturbation. You put an adversarial collar on this dog, and that will might suppress this bounding box. But then non-maximum suppression will just choose the next most confident bounding box. And if you suppress that bounding box, then non-maximum suppression would choose the next most confident bounding box. And so if 500 bounding boxes detect this dog, you have to defeat all of them, right? Every one of those different detectors at different locations with different bounding box aspect ratios have to be defeated. Otherwise, this dog will still show up. And that makes it much more difficult to defeat a detector than it is to defeat a classifier. And as a result, there's been some literature of people claiming that it's really hard to defeat detectors. I think to an extent they're right, it is hard to defeat detectors. Like this paper, no need to worry about adversarial examples in object detection, and standard detectors aren't currently fooled by adversarial stop signs. But there's been some rebuttals to this. For example, fooling automated surveillance cameras. This is an example, a paper where they put, they print out adversarial posters, and in some situations they're able to defeat an object detector. An adversarial t-shirt, they create a t-shirt that is able to defeat a detector, but the t-shirt is custom designed for a particular person and a particular background. And I think this is actually really terrific work. But one of the things we're interested in is, can you just make a generic t-shirt that any person can put on in any situation that can defeat an object detector? And so this is the result of our, this is one of the things that we've been working on in our lab. And to do this, we created a more sophisticated adversarial example crafting pipeline. So what we do is we actually train our adversarial examples. We don't just craft them for a particular image, we actually train them on a data set. So we load up the COCO data set, COCO object detection data set. It's got about 150,000 images. And we load each image up, and then we run the YOLO detector on it. And that produces all these bounding boxes for people. And then you can see this output feature map. Remember, there's that 40 by 60 grid, and it has these red dots that show up at the locations where it's confident that there are people. And then what we do is we render an adversarial pattern over all of these people, and then we do a gradient descent step to update that pattern to squish all of those confidences down so nothing shows up with high enough confidence anymore that it will set off the detector. And if we actually use this sort of training process, we can create something kind of like this. So this is our invisibility cloak. This is me standing in front of a classroom at University of Maryland. You'll see that YOLO detector puts blue bounding boxes around all of these people sitting in the background, but it doesn't put a blue bounding box around me, even though I'm standing right in the middle of the image, and it's because I'm wearing this, this adversarial shirt. So you might look at the shirt and think, well, any shirt with a weird pattern might defeat this detector, but it turns out you really need a very specialized pattern to defeat these kinds of detectors. So for example, if you were to wear a shirt like this that camouflages you into your surroundings, that these sorts of camouflage images generally don't defeat detectors. Detectors tend to be better than humans at finding camouflaged people. So this gets detected by the YOLO detector. You could, for example, wear a onesie with all sorts of different patterns that cover your entire body, and then stand in front of a background like this that has colors and patterns that are similar to the onesie. We took an entire photo shoot in this setting, and we found that we were able to detect the person in these photos consistently. Actually, every image we took, we were able to detect this person using the YOLO detector. And here's another interesting demonstration. If I hold this adversarial poster in front of me, I disappear from this image, but then if I flip the poster upside down, I come back. So this adversarial pattern has almost no adversarial effect at all if I turn it upside down. And so it really takes a carefully crafted adversarial pattern to defeat these kinds of things. And one thing I'll mention, we've also looked at interpretable scenes that look a lot like this image. So we've looked at posters that contain, for example, people standing in a field or people walking through a market, other kinds of interpretable scenes with similar looking features that we found on the internet, and they also have very little adversarial effect. So here's a, we were not able to make a full-scale demo of this, unfortunately, because of the COVID shutdown happened right as we were preparing to film. But me and Zhuxuan, who was the lead author on this work, we have some I guess, practice footage that we made right before the shutdown. So here's just the footage that we have. So this is running the YOLO 2 detector. And you'll see the bounding box around me disappears when I pick up that adversarial shirt. You'll also see there's somebody sitting in the background here that gets detected, and actually the blast radius of the shirt is wide enough that oftentimes that person disappears from the image as well. All right. So there's our work on the invisibility cloak. So I've talked a bunch about how you can break these kinds of systems. But one thing we're also interested in is how can you use adversarial examples to make classifiers better? So how can we actually improve vision systems using? Yes.
Quick question there.
Yeah.
So one of the outputs of YOLO for each bounding box is a prediction of the probability that that is an object or not. And as you said, data is what allows one to do the ranking and just keep the top so many. For those videos, for instance, would you be able to plot what those probabilities are? Say for the, let's say you could just mark the correct region where the bounding boxes are and just take all bounding boxes that are supposed to detect you and then plot them as a function of time to actually see that those probabilities are the ones that are going down. Or to essentially try to debug what is it that is happening.
To see, okay, so we haven't done something where we look at what happens over time. In our paper, we do visualize some of these feature maps. So these are actual feature maps from the YOLO detector here. So this is actually the original feature map for this image. And then this is the feature map with all of these patches rendered over it. And we do visualize some of this. I'll just point out some of these, just because you see these dots here doesn't mean that they're actually over the detection threshold for YOLO. The detection, you can see the color bar here. The detection threshold, the default detection threshold for YOLO is 0, right? So these things are all actually still in the negative. But we do look at what happens to feature maps. When you say over time, I'm not actually sure what you mean by over time. You mean as a train?
Because it was a video, right? So you were producing a bounding box or not at every time instant.
Oh, I see. Yeah, you know, we actually have a video demo of this setup where you can stand in front of, or at least we did, where you can stand in front of a camera and you can actually see the heat map, heat map of features when you put the shirt on. One of the things that's interesting is that the way we train these perturbations, when we train these perturbations, we're not actually identifying the individual locations where people are. What we do is we just run the detector, and anywhere the detector finds a person, we'll render a patch. And then what we do is we update the pattern in that patch to minimize the Frobenius norm of this entire objectness score map, right? So you say it outputs an objectness score, what we're actually minimizing is the Frobenius norm of the entire map. And as a result, it's actually not even specific to the individual that the patch is on. It's just optimized to suppress objectness scores over the entire image. And we've actually done some transfer. This is actually I think they appear in the appendix of our paper, but you can actually put these patches on you can put them on like chairs and horses and all sorts of things. And they still work. Actually, it doesn't even have to be a person. In fact, objects that occur, that tend to coincide with people like horses, it works almost as well as it does for people, which I thought was, I thought that's sort of interesting. But yeah, it's a good point though. We do have a demo a video demo where we show these heat maps, but we didn't actually record the heat maps. And that would be really nice to have. If we get a chance to make a real video demo in the future, one of the reasons we haven't is just because making a video, you want there to be people in the background if you're gonna demonstrate an object detector. And we haven't really had a chance to do that. But if we do, it's a really good point. If we do make an official video demo, I think we should capture those heat maps. You can see better what's going on. Okay. One of the issues I want to address is how can we use adversarial attacks to make classifiers better? And so one particular thing that we're interested in is the fragility of classifiers to things like domain shift. We're interested in domain generalization. So if you train a classifier on one domain, does it transfer to another domain? And for things like ImageNet, it turns out that transferability isn't very good. So for example, top 1 accuracy of resonant 50 on ImageNet is about 76%. But if you then stylize, there's a data set called stylized ImageNet, where you just take artistic styles and you restyle ImageNet images into those styles, that accuracy actually degenerates to 14%. So these recognition systems expect really high quality, really brightly colored web images. And when you show them something from a different domain, they tend to fail. And so what we'd like to have is a system where we can create adversarial styles. So this is an adversarially stylized image. So we took this goldfinch and we restyled it to make it into a pinwheel. And by doing this, we actually picked an adversarial stylization. So we made a stylization that has the most dramatic effect on the class label as we can, given the parameters of the restylization that we allow. And then we can do adversarial training in the style domain. So as you're training, you can load up a batch of images. You can create an adversarial style that manipulates the classifier as much as possible. And then you can train on those images to try to create a classifier that is immune to these kinds of changes in image stylization. Okay, so how would we do this? Well, to do this, we need a way to parameterize image styles. Many people actually do restylization using these simple instance normalization methods. And the way they work is they parameterize styles just by looking at the mean and standard deviation of feature maps that are extracted from an image. So you typically would take an image, you'll push it through a VGG-based encoder that produces 512 feature maps, and then you have a mean and a standard deviation for each of those feature maps. If you want to restyle this image, so this is like a Cynthia image, and we're going to restyle it to look like a cityscapes image. So you take this real image and you extract the mean and standard deviation from the feature maps in this image. And then I'm just going to rescale the feature maps in the target image so that they have the same mean and standard deviation as the style image. So you're just going to renormalize it to have the same feature map statistics as the style image that you want to use as a source. And then you can use a decoder to reconstruct these renormalized feature maps into something that has the correct style. So the thing that's great about these instance normalization methods is it allows you to use only about 1,000 values to parameterize the space of image styles. You just need the mean and standard deviation for each VGG feature map. There's 512 feature maps. That gives you 1024 values that parameterize the space of styles. And we can do adversarial training in that space. So we can load up an image at training time, and then we can apply, we can adversarially choose these means and standard deviations, right? So we're going to optimize these means and standard deviations to break the classifier as much as possible when the classifier is acting on this output image, and that will give us an adversarial style, and then we can use that to adversarially train the network. So we can train the network on these restyled images and make it robust to these fairly severe changes in image style. So here's some examples of that. So these are adversarially restyled image. You got this, these are just some images that we chose from ImageNet. So you have like this, paper mache turtle that gets restylized to look a bit artistic. You get this dog where you remove some of the patterns. Sometimes it makes things look a bit cartoony, but sometimes it doesn't. That doesn't seem to happen to this pepper. It actually just kind of smooths it out a bit. And sometimes you'll get interesting changes to the textures. So for example, the texture of the clouds in the background of this image versus the texture in the adversarially restylized image. We can also control how severe the perturbations are. So we can have an epsilon that controls the size of the relative perturbation you can make to the mean and standard deviation. And that allows us to take, say, these original images, and then we can make the restylization stronger and stronger and stronger. And we can basically turn a knob to control how severe of a restylization we would like. And using these sort of adversarial training methods, we actually get pretty good results on some domain generalization data sets. So for example, on the ImageNet Instagram data set and the stylized ImageNet data set, we can currently get state-of-the-art results. So this is a data set where we take Instagram and we apply, or we take ImageNet images, and we apply Instagram filters to them before we classify them. And then there's also stylized ImageNet where you apply artistic styles to these ImageNet images. We can create systems without having to train. For example, some of these other existing methods will actually train on a huge battery of different data augmentations. We don't even have to, parameterize or handcraft the data augmentations that we want to train against. We're just doing adversarial training to make the system as robust as possible to any domain shift that's parameterizable by one of these instance renormalization methods. I think there's a question. I can't see it, unfortunately, the way my display is set up. So if there's a question, someone should just feel free to jump in and interrupt me.
Yes, happy to read it for you. When you generate adversarial samples, do you fool the Amazon and Microsoft system? How did you get the gradients to update your samples?
Okay, so rewinding a bit to the LOWKEY system, we don't know. That's a black box attack, which means we don't know how the system works. So what we did is we ensemble. Let me rewind to that a bit. So one of the things that I mentioned here is that we ensemble over, when we train, we basically attack a white box model. So we ensemble over different architectures and different backbones and different pre-processing pipelines, and we create an adversarial attack that breaks all of them. And now we hope that that transfers to systems that we haven't seen. So we then took these attacks that we crafted on our own white box system, right? So we know how our system works and we can get the gradients for it. And then we deployed it against these industrial systems and it transfers, right? So we're not able to actually craft attack against these systems because we don't have white box access. So we craft an attack against a huge battery of model systems that we created. And then we hope that some of those hit close enough to the actual industrial systems that will get transferability. And we find that we do get good transferability in this case.
Yes.
So that's a black box. We're not using any gradients.
Yes, I'm gonna, there is a follow-up question from the same person. I'm not so sure it's pertinent, but I'll read it in any case. Follow up on the same question is, if they block you from getting this info, do you have to try too many times for each adversarial sample, which makes it practically impossible? I guess.
Right, so because it's a transfer attack, we're not using the outputs from these systems to develop the attack, right? So we just developed the attack completely on our own model system, and then we deployed it against these industrial systems. And actually, we didn't do any significant, we didn't do much engineering to try to break these systems. We did try a few different methods for bounding the perturbations, but actually some of these face recognition systems are more fragile than I had expected them to be. I expected them to be quite resilient, actually, and we were surprised at how fragile they were. But yeah, without actually using the outputs of the system, we were able to get pretty good transferability. Okay, so moving on, I'm going to talk about a different kind of threat model. I'm going to talk about poisoning. So poisoning means that you're going to make perturbations to the training data that an organization is using in order to manipulate their system. So you might wonder, when does this actually happen, right? If an adversary has access to your training data, they can make anything happen. If they want to make me change my identity to Matt Damon, you just put pictures of me in the training data set and label me as Matt Damon, and then you'll have a system that thinks I'm Matt Damon. So if the adversary can manipulate your training data, that might seem like too strong of a threat model, but it's actually not necessarily such a strong threat model. There are situations where you give outsiders all sorts of access to your training data without even thinking about it. For example, if you're scraping images from the web, anyone can put images on the internet and wait for them to get scraped and labeled. And oftentimes, even if they're labeled correctly, they still have adversarial effects. You might harvest system inputs, like you might have a spam detector where people send emails to your organization. Anyone can email your organization, and then people label the emails as spam or not spam, and they get harvested and collected to update the spam detector. You can also have potentially bad actors or inside agents that want to poison your data in such a way that it's very difficult to audit. So how would you actually, so the kinds of poisoning attacks that we're interested in, there's a big literature on poisoning attacks. The ones we're interested in are called clean label attacks. So you're going to make a modification to an image that makes it into a poison, so you can control the outputs of the classifier that's trained on it, but you still want the image to be labeled correctly. So you want it to be something that looks like a frog, it looks like a normal frog, but it's actually a poison frog, right? If you look at the image, you might not notice the difference. And this might be labeled correctly as a frog, it still has poison effects. And we also are going to look at systems that are targeted. So we're only going to change the test time behavior of a system on images that are selected by the attacker. And these two properties make it relatively easy for an outsider to execute these kinds of attacks without very much control over what the data set looks like. So the first kind of attacks that we're interested in are what are called feature collision attacks. And these work in a situation where you know what feature extractor is being used, or at least you can guess. And you are going to you're going to assume that we're working with a system that fine tunes a layer or two on top of a feature extractor. So this is the transfer learning scenario. And in situations where you have very little data to work with, it's actually fairly common to use a pre-trained feature extractor and then fine tune on top of that. So what we do is we have a base image. So we pick a frog, and we have a target image. So we have this airplane, and we're going to try to make a poison frog that attacks this airplane. So we solve an optimization problem. We got the base image, this is the frog, and there's two terms in the optimization problem. The first one says that the poison image X needs to be close to the base image in pixel space. So to you and me, it still looks like a frog. But then in feature space, I want the feature space representation to look like the feature space representation of the target image. So in feature space, the image looks like an airplane. So we solve this optimization problem, and we can create an image that looks like a frog to you and me, but in the feature space of the neural network, it lands in exactly the same space that this target image is going to when this target image eventually comes along at test time. And then when we train on this image, neural networks tend to have very fluid boundaries and usually overfit on your data. So the decision boundaries are going to move to accommodate the fact that you have an image at this location in feature space that's labeled as a frog. Now at test time, this airplane comes along and it lands in this exact same location, and the decision boundaries at this location say that this is a frog, right? So this test time image will get labeled as a frog. We call this the one-shot kill attack because you only need one poison image to do it. And here's a demonstration of that. If we train an ImageNet classifier, it labels all of these things up here as fish. And if we then add just one single poison image to the data set, we can change the identities of these different images. So here's the original ImageNet image. If I add this poison image, so this is a poison dog, it's slightly different than the original dog. If we add this poison dog to the training set, just this one image, then at test time, this image changes its identity to dog. And if we add this poison image to the data set, then this becomes a dog. And we can make a poison image for all of these test images. And just to show it didn't cherry pick too badly, I'm going to reverse the roles here, and I can use these poison fish to change the identities of these dogs. So each of these poison fish makes one of these dogs into a fish at test time if it's present in the data set. Okay, so one thing we've been interested in now is how can we push poisoning into the future? What can we do just beyond the simple kinds of demonstrations we've already done? One thing we're interested in is it possible to poison end-to-end training? So far, most of the cleanable poisoning attacks that have been demonstrated have just been on these transfer learning scenarios. Can you get it to work with any set of base images? Can you get it to work with any attacker objective? Maybe it's not just simply relabeling an image. And can you scale this up to break industrial systems? And so our recent work has focused on these more sophisticated kinds of attacks. So this is one called metapoisoning. Metapoisoning takes ideas from the meta-learning literature. In the meta-learning literature, you have training methods that backprop through the training process. So you might have a pipeline where you do SGD and then you backprop through SGD, and that's exactly what happens in this metapoison framework. So here's how it works. we're going to form a model of the victim, and the victim has a whole bunch of training data. So it has a bunch of training data, and maybe there's a few poison images floating around inside of that training data set that the victim doesn't know about. And I want to figure out what these poison images should be to maximize their effects. So we run a simulated training process where we do this. We form a mini batch. So I'm going to randomly sample some of these clean images, and then maybe my mini batch incorporates, one or two poisons. Maybe it doesn't. We want a random batching process to get something as close as possible to the real training process. So we sample a mini batch that may contain some poisons, and then we use it in a training algorithm. So we start with some network parameters. We run an iteration of SGD using this batch, and then we output theta prime. This is the updated parameters. Right, so we simulate an iteration of SGD that the victim would do. And now the attacker looks at those output parameters and evaluates whether or not they accomplish the adversarial objective. So for example, maybe this measures whether or not airplanes are correct or classified incorrectly, or it measures whether someone's identity has been changed the way that the attacker would like. So the attacker simulates the training process and then evaluates whether or not their attacker objective was accomplished using the output of SGD. And then we backprop through that entire thing. So we take the derivative of the adversarial loss all the way through this SGD training process, and then back to the poison images that were input in this batch. So we figure out for every pixel in this poison image, how does it affect the adversarial loss after it is used for training? So we backprop through the training process, and then we can make an update to this frog to make it into a poison frog that will manipulate the training process. So here's some example of some of these poison dogs. Right, so over here we have these clean dogs, and we have poison dogs on this side. And you'll see this is so this is done on CFAR, and a lot of our original experiments were done on CFAR because end-to-end poisoning is really expensive. If you want to do a single trial run, you have to train a neural network from scratch. And so a lot of our early work was done on CFAR. And we can use these poison images to change this bird into a dog. We also find that these kinds of metapoisoning methods are fairly transferable. So this is showing if we use these different attacker networks on these different victim networks, what kind of transferability do we get? And in some situations, you get really good transferability. So for example, a ResNet 20 model, it gets 72%. If you attack a ResNet 20 model, then your attack will succeed 72% of the time if you poison 1/10 of 1% of the data. If you try to craft your attack on a ResNet 20 and then deploy it on a simple 4-layer CompNet, it still works 63% of the time. And if you craft your attack on ResNet 20 and you deploy it on VGG 13, it works 84% of the time. So actually transferability for these kinds of things is quite good, which made us wonder if this will transfer to industrial systems. So all these kinds of simple attacks, they're a bit idealized, but can they transfer to industrial systems? And what we found is that sometimes at least they do. So this is one of our first examples. This is using CFAR. And so what we did is we took the CFAR data set, we poisoned 0.2% of the images with an imperceptible poison, and then we uploaded this to Google AutoML. So Google AutoML is a proprietary tool. It actually does a neural architecture search to find a neural network architecture that's good for your data set. And so this is the ultimate black box. I don't know what family of architectures are being searched. I don't know what search algorithm they're using. I don't know what optimizer they use. Is it Atom? Is it SGD? Is it some proprietary thing? I think it's probably proprietary. What learning rate schedule do they use? What batching strategy do they use? Do they use dropout? Do they use momentum? Do they use weight decay? Right? We don't know any of these things. It's just a complete black box system. But what we find is it's actually possible to poison these data sets and then upload it to AutoML and succeed. So for example, in this case, this is the target image of the bird. We can swap its identity to being a dog just by crafting a poison on our own white box model and then transferring it to this black box system. And then finally, we've recently worked on scaling these kinds of methods up to larger and larger sizes. So we just recently had this paper submission, which is brew industrial scale data poisoning via gradient matching. And this makes some major improvements over the original metapoisoning framework in order to scale it up to larger data sets and get it to work very efficiently. And And so these are some examples. It also tends to work well without ensembling. And so without ensembling, we're able to get this attack to work at the ImageNet scale. So we poisoned 1/10 of 1% of the images in ImageNet. So here's some clean images and here's some poison images. And then we uploaded the ImageNet data set to Google's AutoML system and we let it crunch for a couple of days. And what we got back was a classifier. Now this attack does not always work, but we were able to get back a classifier where this otter its label is changed to dog. So we chose this otter at random and we were able to change its label to a dog. Right, so at least that's a proof of concept that these things do transfer to industrial systems. Now, doing large-scale testing and optimizing this kind of system for AutoML is a little bit beyond our means because every one of these trial runs on AutoML costs about $1,000. So we're not able to do a really thorough investigation, but we are able to show that we were able to poison the ImageNet data set and push that through AutoML, and these poison perturbations actually survived. And then finally, one last thing I wanted to mention, if you're interested in poisoning attacks, one of my students, Avi Schwarzschild, worked very hard to create this, this poisoning benchmark, right? So he has a paper called Just How Toxic is Data Poisoning, and it talks about all of the issues in evaluating poisoning methods. It's very difficult to do a thorough evaluation of the effectiveness of poisons. And he actually creates this poison benchmark where he benchmark a variety of different poisoning attacks against white box attacks where they can see the training process, the gray box where they can see some things about the training process, and then a complete black box scenarios where you don't get to know anything about the training process at the time that you're crafting your attack. And so, yeah, this is interesting, framework for evaluating how effective we can get these poisoning attacks to be. Okay, so I will wrap up. I just want to say thank you very much to all of the students and postdocs that I have worked with. Most of the work that I presented is actually work from these folks who did an amazing job on all of their projects. Some of these folks are still in my lab. Ali Shafahi recently left for Apple. Ronnie still works in my lab occasionally, but he recently moved to Google Research. And then Micah has transitioned to being a postdoc. Actually, Jonas is about to graduate soon as well. Oh, and Zishuan is now at Facebook. So some of these folks are no longer in the lab, but we really benefited a ton from having all the terrific work that these folks did. If you're interested in some of the work I talked about today, here's a list of papers that I spoke about. And with that, I will call it quits, and I'll take any questions you guys might have.
Thank you, Tom, for a really great and inspiring talk. Again, if you've got any questions, please put them on the chat, and we'll be taking questions now. So let me get maybe the question started. I think it's fairly clear, and I think you've provided many examples of how one can attack AI systems. The question I have is more from the perspective of whether in reality, one would always have access to the information to be able to craft those attacks. I guess the more from a theoretical perspective, whether there shouldn't be some sort of framework like in game theory, that is like a zero-sum game, where there are constraints on the attacks and constraints on the defense mechanisms that allow for having equilibrium, as opposed to setting up for situations where the attacker can always win. You show many examples where performance was 90-something% and you could get it to 1%. And why are we, from a theoretical perspective, allowing it to be in situations where maybe too much access is given to the attacker?
Huh. So what do you mean by access? That's the question.
Well, information, like you can compute the full gradient, or you can have access to the entire training set, or you can modify the training objective.
Yeah,
maybe quoting Ramachelapa is like, I give you the keys to my house. So right. You kind of steal.
I think a really unsatisfying answer to security people is, one of the best kinds of security in this space is just security by obscurity. if the attacker doesn't know the system they're attacking, sometimes the attack is really difficult. And I think in the classical security world, that's considered very unsatisfying. But in the ML world, in a lot of ways, that's the only security guarantees that we've really been able to have. And you know, keeping systems proprietary. So for example, systems like Content ID, I think it's really important that they stay proprietary. I don't know how it works. I'm fairly confident that it's a ComNet-based system. And if it were exposed, if someone were to get access to a white box model for that system, I have to imagine that breaking it would be very easy. And so there's a situation where I think, you know, this security by obscurity provides some security. So like you said, like you need some sort of insider access to execute those attacks. Interestingly though, there's also systems where you don't seem to need any access. And one, you know, because you get great transferability. And one thing I've really been curious about lately is what's the difference? I don't understand what the difference is. So for example, these face recognition systems transferred really well to Amazon Recognition and Microsoft Azure for some reason. And I don't know why. You know, is it because our surrogate models were really close to the actual implementations? Or is it because these systems just have lots and lots of really transferable adversarial examples? I'm not really sure what the answer is, but in that situation, you don't seem to need any real insider knowledge. Like a simple ensemble is of 4 different networks is already enough to transfer really well to these industrial systems. And whatever they're using, I'm very confident it's not just an off-the-shelf system. I actually have students that work on the Amazon Recognition API, and I haven't spoken to them at all about the details of the system, but I know they have a ton of experts in there that have built a really sophisticated, customized system. And then in other situations, you need a huge amount of information to make these attacks succeed. Like for example, trying to break the YOLO detector is really, really hard, and those attacks do not transfer very well. We studied the transferability of these attacks in our paper, and we find that they don't transfer very well across systems. Now, if we could identify what, when these attacks transfer and when they don't, what properties of systems lend them to transfer attacks, or what kinds of adversarial attack pipelines are most effective for attack transfer. If we can understand that, then we might be able to have leverage that to build systems that we don't have to worry about being black boxed. But that's a big hole, at least it's a big hole in my understanding, that where I just don't quite understand what's going on. I know there's some theory being developed, right? I believe your lab is actually working a bit on these transferability problems. I know Bo Lee also has some interesting theoretical results about guaranteeing that in certain situations attacks transfer. But empirically, I don't have any understanding for why it works so well in some situations and not in others.
The other question I had was about ensemble methods, both for defenses and attacks. So on the defense side, you were arguing how YOLO detectors are intrinsically more robust because they just produce multiple hypotheses. But more broadly, you could think of ensemble methods where you've got multiple different models even for classification, and then you do an ensemble. Are there any advantages? Is there any theoretical work showing that ensemble methods would be more robust? And if that, how do you put that at odds with the example that you were providing, that you put that sweater and you still break a detector? I mean, why? Yeah. I still don't understand why the sweater breaks the detector.
Yeah, I don't completely understand either. I think you mentioned once before that it looks like maybe it's just putting like people, on it.
In the sweater, yes.
I mentioned there's also other patterns that we can get with different backbones that don't have anything that even looks remotely like that. So yeah, ensembling is surprisingly powerful, and I don't have a complete understanding of why. My sense is that there's different kinds of adversarial examples. There's adversarial examples that sort of arise by accident, like you randomly initialize your network, and then after you train, there are artifacts that are a result of the random initialization. and that are not reproducible across networks. And those are exploitable, right? Whereas if you do a ton of ensembling, then you can't routinely exploit any of those artifacts anymore. And the only kinds of adversarial attacks you can craft are things that are reflected by ambiguities that arise in your data set. So they're sort of fundamental adversarial examples. And what I find is that if you actually try to attack, a lot of people have found this, I think, if you try to attack an ensemble, let's say you look at image classifiers. If you attack a single classifier on ImageNet, you can just add a little bit of adversarial quote unquote noise and break the classifier. But if you try to attack an ensemble of classifiers, suddenly the perturbations you make start to be really interpretable. Like I was trying to make a cow into a traffic light at one point, and I just tried attacking an ensemble of all the standard PyTorch models. And I found that it actually started making the cow into a traffic light, like its knee would turn into like a bright green light. And so attacking ensembles is really tough. And in order to do it, it seems that you have to actually change the semantic properties of the images. The reason why the YOLO detector, why we're able to break that, so I'd point out it's really hard to break the YOLO detector, and the level of reliability we get is not 100%. And you'll see even in the video that I showed, there are frames and things where I pop back into the frame. It's not 100% effective. And the only reason we're able to break it at all is because you can make an interpretable and arbitrarily large perturbation, right? I have this huge perturbation on my entire shirt. It wouldn't work. We tried it with smaller posters. It doesn't work if I just have like an 8.5 by 11 sheet of paper. It doesn't work reliably. We have a lot of pixels to manipulate. We can manipulate them as far as we want. It doesn't have to be imperceptible. And what we find that comes out is completely structured and interpretable adversarial examples. They look kind of like blurry images, right? They don't look like adversarial noise. And so these attacks I don't think it contradicts the hypothesis that ensembles are robust. I think it just reinforces that hypothesis. You have to use huge, structured, interpretable adversarial perturbations in order to break those systems. And even when you succeed in breaking them, it's not reliable behavior.
Yeah. Great. Well, I don't think I see any other questions. So if anyone else has a question, please let me know soon. Otherwise, we'll be closing the session. Let me see. No. Well, Tom, it's always a pleasure to hear you. It was a very nice presentation. Thank you very much. And thank you to